From today onwards, we are going to start a new chapter called Biomolecules, and this is the 14th chapter of your organic chemistry textbook. In this chapter, we are going to study about some of the important molecules which are responsible for proper functioning of a living system. The word biomolecules itself indicates bio refers to life or living, and then the molecules. So molecules which are present in living system is called as biomolecules. To give you some of the examples of biomolecules, there is carbohydrates, which acts as a source of energy, and then there is proteins which are responsible for building of muscles, and then there is vitamins, deficiency of which causes different types of diseases, and then there is nucleic acids, which includes RNA and DNA, which is responsible for genetic makeup of an organism. And then there is hormones, enzymes, fats, all this comes under biomolecules. So in this chapter, in particularly, we are going to study about carbohydrates, and then proteins, then you'll have vitamins, and nucleic acids. So we'll be going one by one, and in each of this case we are going to study about their definition, their structure, and their classification. So we'll go one by one now. Let's begin with first carbohydrates. So to define carbohydrates, it has got two definitions. The first one is classical definition and the second one is modern definition. According to the classical definition, it is defined as hydrates of carbon. From the name itself, it indicates carbohydrates or hydrates of carbon, which has the general formula of CX times and then H2O Y times. Now, according to this, all the carbohydrates should fit into this formula. For example, glucose, which has the molecular formula of C6H12O6. When you write this in the form of this formula, this will become C6H2O 6 times. But the problem with this definition is that all the carbohydrates does not fit into this formula. For example, rhamnose, which has the molecular formula of C6H12O5, it does not fit into this formula. And non-carbohydrates compounds like acetic acid, which has the molecular formula of CH3COOH. Acetic acid is not a carbohydrate. But this fits exactly into this formula. So this can be written as C2H2O 2 times. Therefore, the problem with this definition is not all carbohydrates fits into this formula, whereas non-carbohydrate compounds like acetic acid fits into this formula. So therefore, this definition was modified, and now the modern definition of carbohydrate is, it is defined as optically active polyhydroxy aldehydes or ketones or compounds which produces such units on hydrolysis. They are defined as optically active polyhydroxyaldehydes or ketones or compounds which produces such units on hydrolysis. So in this case, first you need to understand what you mean by optically active compounds. If you remember, we have already done this in class 11. Optically active compounds are the compounds which rotates the plane of polarized light towards either clockwise direction or anti-clockwise direction. Now in this case, a compound to show optical activity, it should have a chiral carbon atom. Now chiral carbon atom are the carbons which is surrounded by 4 different groups. In the case of glyceraldehyde, where you have a carbon, then you have OH, CH2OH, an aldehyde, and then you have hydrogen atom. So in this case, this carbon is surrounded by 4 groups which are different from one another. So compounds which contains a chiral carbon atom are said to be optically active because it rotates the plane of polarized light towards either clockwise direction or anti-clockwise direction. So carbohydrates compounds are said to be optically active. Also, they contain polyhydroxy groups. Poly means many, so they contains many OH groups. Hydroxy group refers to the OH. Now let me give an example for this definition. Let's take again the most common example, glucose. Now let me write down the structure of glucose first. Glucose has an aldehyde group, CHO, and it has the molecular formula of C6H12O6. First carbon, second, third, fourth, fifth, and sixth. The sixth one has got a primary alcohol, and then you have second carbon, OH on the right, hydrogen. The third carbon will have OH on the left hand side, and then you have a hydrogen. And then the next one will have OH on the right hand side, H and H. Now if you look at the structure of glucose, you can see that it is a compound which aldehyde adds the functional group, and also it has polyhydroxyl groups, that is 1 OH, 2, 3, 4 and 5 OH groups. So these groups are called as polyhydroxyl compounds. So optically active polyhydroxy aldehydes or ketone. Glucose is a polyhydroxy compound which has aldehyde as the functional group, and they are optically active because look at this carbon. This carbon is surrounded by one group. This is the second group, this is the third group, and this is the fourth group. So this carbon is a chiral carbon atom. So they are optically active because it contains chiral carbon atom, and they contains polyhydroxyl groups, and they have aldehyde or ketone as the functional group. So this is one example of carbohydrates. So that's about the definition of carbohydrates, which says they are optically active polyhydroxy aldehydes or ketones or compounds which produces such units on hydrolysis. Hydrolysis means breakdown with the help of water molecules. So that's about the definition. Now let's move to the classification of carbohydrates. Classification of carbohydrates can be done in few different ways. The first one is based on the number of monosaccharides produced on hydrolysis. Okay, so first you need to understand what is monosaccharides. Saccharides is derived from the Latin word saccharine, which stands for sugar. So glucose is an example of monosaccharide. Fructose is an example of monosaccharide. Now in this case, classification based on the number of monosaccharides produced on hydrolysis. So it means monosaccharides like glucose, fructose, it is just one. You cannot break it into more number of monosaccharides because it is the smallest unit of a carbohydrate. Similarly, there's fructose, which is again a monosaccharide, and ribose is also a monosaccharide. Now what happens is Starch, when you hydrolyze, you get n number of monosaccharides. When you break down the starch, you will get many number of monosaccharides, because starch consists of, or it is built up of many monosaccharides coming together. So based on the number of monosaccharides produced on hydrolysis, it can be further classified into monosaccharides, and then there is oligosaccharides, and then you have polysaccharides. Poly means many or more than 10. Many refers to more than 10. Oligo refers to 2 to 10. And mono means just one. So in this case, monosaccharides, they cannot be further hydrolyzed to give you more number of monosaccharides, because it is just one unit. So example of monosaccharides is glucose, fructose and ribose. Okay, I will say it cannot be further hydrolyzed. For example, there is glucose, fructose and ribose. Okay, I'll go one by one. Examples for monosaccharides is glucose and fructose. Both of these have same molecular formula, that is C6H12O6. So monosaccharides are the carbohydrates which cannot be further hydrolyzed. Example is glucose and fructose. You also have ribose. Now the next one is oligosaccharides. Now oligosaccharides are the carbohydrates. On hydrolysis, it gives 2 to 10 units of monosaccharides. Now example for this is sucrose, the sugar that we use, sucrose, the table sugar, and then you have lactose, sugar which is present in milk, and then there is maltose. These are example of oligosaccharides. Now sucrose is made up of 2 units of monosaccharides. So on hydrolysis it gives glucose and fructose. Similarly, lactose is a disaccharide. Disaccharide means which on hydrolysis it gives 2 units of monosaccharides. So under oligosaccharides you have disaccharide which gives 2 units of monosaccharides on hydrolysis, and then there is trisaccharide which gives 3 units of monosaccharides on hydrolysis, and then there is tetrasaccharides, pentasaccharides goes on till 10. So that's about oligosaccharides. Now the next one is polysaccharides. So polysaccharides are the carbohydrates which gives more than 10 units. More than 10 units of monosaccharides. Monosaccharides on hydrolysis. So example for polysaccharides is you have starch that we obtain from our foods, and then you have glycogen which acts as energy storage in animals. Starch, glycogen, and then there is cellulose which is present in the cell walls of plants. Cellulose. So this is about the first classification of carbohydrates based on the number of monosaccharides produced on hydrolysis. So out of this, the important carbohydrates that we are going to study in detail is from monosaccharides. we are going to study in detail about the glucose and fructose. We are going to study about the preparation of glucose and fructose. We are going to study about the structure of glucose and fructose. And then the next one is from oligosaccharides. From oligosaccharides, we are going to study in detail about sucrose, lactose, and maltose. And from polysaccharides, we are going to study in detail about the starch, cellulose, and glycogen. So these are the important carbohydrates that we are going to study. Now that we are done with classification of carbohydrates, now let's go into detail of monosaccharides, then we'll go to oligosaccharides, then finally the polysaccharides. So let's start with the monosaccharides. Now there are different number of or different types of monosaccharides depending upon the number of carbon atoms present in them. The least number of carbon atoms present in a monosaccharide is 3 carbon atoms, because when you say polyhydroxy compounds, 2 or 1 carbon atom is not enough, so at least it needs 3 carbon atoms. If 3 carbon atoms are present, the general term uses triose. If it is 4 carbon atom, tetrose. Now, depending upon the functional group present again, if aldehyde group is present with 3 carbon atom, then it is called as aldotriose. If ketone is present, then it is called as ketotriose. Monosaccharide is ketotriose. If ketone group is present, it is aldotriose if aldehyde group is present. Similarly, if you have 4 carbon atoms, the general term is tetrose, and if aldehyde is the functional group, it will be aldotetrose. Okay, then, sorry, R is there, tetrose. Tetrose. If ketone group is present, then it will be ketotetrose. If it is 5 carbon atom, it will be pentose, and this will be aldopentose if aldehyde group is the functional group. This will be ketopentose. Similarly, if you have 6 carbon atom, this will be hexose, and this will be aldohexose, and this will be ketohexose. So the 2 monosaccharides that we are going to study, that is glucose and fructose. Glucose is aldohexose, C6H12O6, that is glucose is an aldohexose because it contains 6 carbon atom, and the functional group present is aldehyde, therefore it is a aldohexose. Whereas fructose is an example of ketohexose because this also contains 6 carbon atom, but the functional group present is ketone. So this is about the different types of monosaccharides based on the number of carbon atoms present. Now we are going to study in detail about the monosaccharides, glucose and fructose. So we'll start with the glucose first. The first monosaccharide that we are going to discuss in detail is glucose. We know that the glucose has the molecular formula of C6H12O6, and glucose is an aldohexose, which means it has 6 carbon atoms and it has aldehyde as the functional group. It is also a dextrose, meaning it rotates the plane of polarized light towards the clockwise direction. So now let's move to the preparation of glucose. Now, glucose can be prepared from sucrose because sucrose is made up of two monosaccharides, that is fructose and glucose, and it can also be prepared from starch or cellulose, which are also made up of glucose. Now, first one is preparation from sucrose. Sucrose on hydrolysis, that is C12H22O11 on hydrolysis, that is acetic hydrolysis, it gives glucose, that is C6H12O6 plus fructose, C6H12O6. It gives 1 unit of glucose plus 1 unit of fructose. So this is about preparation of glucose from sucrose. Sucrose, which is made up of glucose and fructose, gives back glucose and fructose on hydrolysis. Now, next preparation is from the starch or cellulose. From starch or cellulose. The general formula of starch is C6H10O5 N times on acetic hydrolysis. You get N number of glucose, C6H12O6. Now this is done at the temperature of 393 Kelvin and atmospheric pressure of 2 to 3 atmospheric pressure. Now this is called as starch or cellulose. Both are made up of glucose. So from starch or cellulose, both are made up of glucose. That's why on hydrolysis it gives back the monosaccharides glucose. So that's about the preparation of glucose. Okay, now let us come to the structure of glucose. Before I go into detail about the development of the structure, let me give you an overall idea about the different ways of writing the structure of glucose. The first one is the open structure. And then there is the cyclic structure and Haworth structure. And Haworth structure. First, let me explain how does an open structure looks like. Glucose has the molecular formula of C6H12O6. Now, the open structure of glucose is written in this way. First, you write a straight chain of carbon atom 1, 2, 3, 4, 5 and 6. Glucose is an aldohexose, which means it has an aldehyde as a functional group. The first carbon carries the functional group, and then you have the second, third, fourth, fifth and the sixth carbon. First has the functional group. Sixth carbon is a primary alcohol, CH2OH. We know that it is a polyhydroxy compound, which means it has more number of hydroxyl groups. Now on the second carbon atom, OH is on the right hand side, H is on the left hand side. On the third carbon, OH is on the left hand side, and then you have H on the right hand side. The fourth and fifth will have OH on the right hand side, and hydrogen on the left, hydrogen on the left. This is the open structure of glucose. Depending upon the position of OH on this carbon atom, that is the second last carbon atom, there are two types of glucose. The first one is D-glucose, and then you have L-glucose. D when OH is on the right side, on the right, and L when OH is on the left, OH on left hand side. So D-glucose and L-glucose, depending upon the hydroxyl group which is present on the fifth carbon atom. If this OH is present on the right hand side, we give the name D-glucose, and if the OH is on the left hand side, we give the name as L-glucose. So in this case, this is a D-glucose. So this is the open structure of a D-glucose. Now if I write down the cyclic structure, in cyclic structure what happens is this OH will react with the aldehyde group. So in this case, this carbon has C double bond OH, bond OH, this is an aldehyde. Now this carbon will react with the hydroxyl group of the fifth carbon atom. So in the process, a ring is being formed between this carbon and this carbon through this oxygen atom. So cyclic structure is written as first, second, third, fourth, fifth and the sixth carbon atom, which is a primary alcohol. Now this has an aldehyde group, hydrogen, and then you have OH on the right. On the third carbon atom, OH is on the left. Only the third carbon atom is on the left. The rest will have OH on the right hand side in the case of D-glucose. Whereas in the case of L-glucose, this OH is on the left hand side. So now I'm writing the cyclic structure of D-glucose. Third carbon atom carries OH on the left, then you have H, and the fourth and the fifth carries OH on the right. Now what happens is this O carries alone two lone pair of electrons, and this pi electron will shift. O will have a negative charge and this carbon will carry a positive charge. Now on this O will bond with this carbon atom O. Now this O will have a positive charge because it loses its lone pair of electrons in forming bonds with this carbon. So in the process, O will have a positive charge and then hydrogen atom. Now this will have O will have a negative charge. Now in order to stabilize the positive charge on the oxygen atom, this hydrogen will leave. This will leave and this will come and attack this oxygen atom. So therefore, this hydrogen will not be there, and instead it will attack this O with a negative charge and it forms a OH. That's how a ring is being formed between this carbon and this carbon. Now when you write down the structure, it is written as this. I just explained the formation of the ring between the first and the fifth carbon atom. Now when you write it in this way. And OH. Now this is the cyclic structure of D-glucose. Now in this case there are again two kinds, alpha D-glucose and beta D-glucose. Now alpha is used when OH is on right. If OH on the first carbon atom is on the right hand side, if it is on the right hand side, we give the name alpha. If the OH is on the left hand side, then we will give it as beta. So alpha D-glucose and beta D-glucose. We have two kinds of glucose depending upon the position of OH on the first carbon atom, that is alpha D-glucose or beta D-glucose. Beta in the case where OH is on the left hand side, alpha when OH is on the right hand side. Now this carbon atom is called as the anomeric carbon atom. Anomeric, A-N-O-M-E-R-I-C, anomeric carbon atom. The reason for this is one carbon is giving rise to two different compounds. If it is OH is on the right hand side, you are getting a alpha D-glucose. If OH is on the left hand side, you are getting a beta D-glucose. So that's why this carbon is called as anomeric carbon atom. A carbon atom which gives rise to two compounds based on the configuration of the groups attached to the carbon atom. Okay, so that's about the cyclic structure. Now if you want to write down the Haworth structure for this, again this is a 6-membered ring. 1, 2, 3, 4, 5, 6. This ring consists of 6 members. Oxygen, 1 oxygen and 5 carbon atom. This also consists of a ring which consists of 1 oxygen and 5 carbon atom. 1, 2, 3, 4, 5. So this is your first carbon atom. First carbon, second carbon, third carbon, fourth and the fifth carbon atom. Here also first carbon, second carbon, third, fourth and the fifth carbon atom. This is your sixth. Now what happens is the ring is formed between first and the fifth carbon atom. Here also the ring is formed between the first and the fifth carbon atom. So from this you can derive the Haworth structure. Now this line, on this line you are supposed to keep these groups. So how do you decide which will come on the top or which will come at the bottom? For that you need to remember that whatever is on the right will go at the bottom, whatever is on the left will come on the top. Right will go to the bottom and the left will come on the top. So first carbon has OH on the right hand side, therefore this will come on the bottom and the hydrogen will come on the top. On the second carbon atom again you have OH on the right hand side, again OH, and then you have your H, and in this case H is on the right hand side, therefore H, OH. On the fourth carbon atom OH is on the right, therefore OH, H. And on the fifth carbon atom, this is the fifth carbon atom which is connected to the first carbon atom through the oxygen atom. So on the fifth carbon atom, this group will always come on the top. So CH2OH and then you have H. Now this is again alpha D glucose. Alpha D glucose because this is derived from alpha D glucose of cyclic structure. The OH is on the right hand side, therefore it is alpha D glucose. From this we have derived this structure, therefore this is also an alpha D glucose. Haworth's alpha D glucose structure. So this is about the structure of alpha D glucose. In the case of beta D glucose, since OH will be on the left hand side, everything is same. Only thing is here OH will be on the left hand side. So this OH will go on the top and this hydrogen will come at the bottom. So that is the difference between alpha and the beta D glucose. Now this is alpha D glucose. Now in the case of beta D glucose, again this is a 6-membered ring. 1 oxygen and 5 carbon atom. This is your first carbon, second carbon, third, fourth and the fifth carbon atom. Now in the case of alpha, OH is on the left hand side. So OH will come on the top and then your hydrogen and rest remains the same. OH, OH, H, CH2OH and H. Now this is beta D glucose. So alpha and beta D glucose. So that's about the overall structure of the glucose. Now we will discuss one by one.